Imagine looking up at the night sky and realizing something deeply unsettling. Every galaxy in the universe is slowly drifting away from every other galaxy, and the farther they are, the faster they move apart. But here's the strange part. This separation isn't slowing down, it's accelerating. For decades, scientists expected gravity to gradually pull the universe back together. After all, gravity attracts everything, from falling apples to orbiting planets. So the expansion of the universe should have been slowing over time. Yet the cosmos had a completely different plan. Observations of distant exploding stars revealed a shocking truth. Some unknown force is stretching space itself, an invisible energy that fills the universe and quietly pushes galaxies apart. Scientists call it dark energy, and it may make up most of the cosmos. But what exactly is dark energy? Why does empty space contain energy at all? And could this mysterious force determine the ultimate fate of the universe? To answer that, we need to journey from exploding stars to the quantum fabric of space itself. For most of the 20th century, scientists imagined the universe like a ball thrown upward. Gravity, they thought, would slowly pull everything back, gradually slowing cosmic expansion. Galaxies might keep drifting apart for a while, but eventually the brakes of gravity would engage. It seemed logical. After all, gravity pulls on everything we know. Picture tossing a stone into the sky. At first it rises quickly, but gravity steadily slows it down until it stops. For decades, astronomers believed the universe behaved the same way. Expansion after the Big Bang should have been gradually decelerating. But then something unexpected began to emerge from observations. When astronomers measured the motion of distant galaxies, the numbers didn't line up. Instead of slowing down, the expansion of the universe seemed to be speeding up. It was as if the cosmic stone wasn't falling back. It was somehow accelerating upward. That realization stunned the scientific community. Gravity pulls things together, not apart. So what invisible influence could be overpowering gravity across the universe? What force could be stretching space itself faster and faster? Somewhere in the vast darkness between galaxies, something strange appears to exist. Something that gently pushes space outward over unimaginable distances. An unseen influence that dominates the cosmos while remaining almost completely hidden. And the first clues of its existence came from distant explosions scattered across the universe. To uncover the secret behind the universe's expansion, astronomers needed reliable cosmic markers, objects bright enough to be seen across billions of light years. Fortunately, the universe occasionally provides exactly that in the form of stellar explosions. These brilliant events are known as Type Ia supernovae. When a star explodes as a Type Ia supernova, it shines with a predictable brightness, almost like a cosmic light bulb with a known wattage. By comparing how bright the explosion appears from Earth, astronomers can estimate its distance. It's similar to judging how far away a street lamp is by how faint its light looks. In the late 1990s, teams of astronomers began measuring dozens of these distant explosions. They expected to see evidence that cosmic expansion was slowing down over time. Instead, the supernovae appeared dimmer and therefore farther away than predicted. The universe had expanded more than scientists thought possible. Imagine watching two ice skaters pushing away from each other on a frozen lake. You would expect friction to gradually slow them down. But what if instead they kept drifting apart faster and faster? That's essentially what the universe appeared to be doing. These distant stellar explosions revealed a shocking pattern across cosmic history. Galaxies were not just moving apart. They were accelerating away from one another. Something unseen was acting across the fabric of space itself. And to understand where that mysterious push might come from, scientists had to look much deeper into the strange physics of empty space itself. To search for the source of this mysterious cosmic push, scientists turned to the smallest scales imaginable, not to galaxies or stars, but to the strange world of quantum physics. At that level, reality behaves in ways that almost feel magical. Even what we call empty space begins to reveal surprising activity. In everyday life, empty space seems completely still, a quiet vacuum between objects, containing nothing at all. But quantum physics paints a very different picture. Space itself behaves more like a restless ocean than a silent void. Tiny fluctuations constantly ripple through this quantum sea. Particles briefly pop into existence and disappear again in fractions of a second. It's almost like bubbles forming and collapsing in boiling water. The vacuum is alive with microscopic bursts of energy. Physicists call this phenomenon vacuum energy. It means that even the emptiest regions of space contain a subtle background energy, and unlike matter or radiation, this energy doesn't dilute as space expands. Instead, it remains embedded in the fabric of space itself. Now imagine the universe as an enormous stretching sheet. If space itself contains energy, then as the sheet grows larger, more of that energy appears with it. Some scientists suspect this hidden energy may be what drives cosmic acceleration. But before its effects become noticeable, we need to zoom out, from the quantum scale to the worlds of planets and stars. If dark energy is pushing space apart, a natural question appears. Why don't we see planets drifting away from the sun? Why doesn't the Earth slowly spiral away into deep space? The answer lies in the incredible strength of gravity at smaller scales. Within planetary systems, gravity completely dominates the motion of objects. The sun's gravity tightly holds the planets in their orbits. It works a bit like a strong rope keeping a spinning ball tied to the center. No gentle cosmic stretching can easily overpower that pull. Imagine an ice skater spinning while holding a heavy weight at the center. The force keeping everything together is far stronger than any small outward drift. In the same way, gravity locks planets into stable paths around their stars. Cosmic expansion simply doesn't have the strength to break that bond. The same rule applies to moons orbiting planets. Earth's gravity firmly holds the moon in its path around us. Even though space itself may be expanding on enormous scales, that expansion is far too weak to separate objects already gravitationally bound. So here on Earth, cosmic acceleration is completely invisible. Day and night continue their rhythm, and planets follow predictable orbits. Dark energy only reveals its influence across the truly vast distances of the universe. And to measure those immense distances, astronomers rely on some of the brightest explosions ever seen in the cosmos. To measure something as enormous as the expansion of the universe, astronomers need reliable cosmic rulers. Distances between galaxies are so vast that ordinary measurement methods simply don't work. Instead, scientists rely on objects whose true brightness is already known. These objects act like cosmic lighthouses scattered across the universe. One of the most powerful tools is the type Ia supernova. When certain stars explode, they reach nearly identical peak brightness every time. It's like thousands of identical light bulbs placed across the cosmos. By seeing how dim they appear from Earth, astronomers can estimate how far away they are. But distance alone isn't enough to understand cosmic expansion. Astronomers also measure something called redshift. As galaxies move away, their light stretches toward the red end of the spectrum. It's similar to the way the sound of a siren deepens as an ambulance drives away. By combining brightness and redshift, scientists can reconstruct cosmic history. They compare how far galaxies are with how quickly they're receding. This allows astronomers to map how the universe has expanded over billions of years. Like reading rings in a tree trunk, the cosmos reveals its past through light. And those measurements revealed something astonishing. The expansion of the universe wasn't slowing down, it was speeding up. Some hidden ingredient seemed to be altering gravity itself on cosmic scales. To understand how that could happen, scientists had to revisit the deepest equations describing space and gravity. To understand how the universe could accelerate, scientists turned back to the work of Albert Einstein. His theory of general relativity describes gravity not as a force pulling objects through space, but as the curvature of space itself. Mass bends spacetime the way a heavy bowling ball bends a stretched rubber sheet. Planets and stars simply follow the curves created by that bending. But Einstein's equations contained something unexpected. They allowed space itself to contain energy, even when no matter was present. That energy could influence how the universe expands or contracts. In certain conditions, it could even act like a kind of cosmic anti-gravity. Imagine placing tiny springs inside the fabric of space. As the universe stretches, those springs push outward instead of resisting. Rather than slowing expansion, they encourage it to continue. This is roughly how scientists visualize the effect of dark energy. Einstein once introduced a term called the cosmological constant to describe this possibility. Later, he abandoned the idea when the universe was discovered to be expanding. But decades afterward, the discovery of accelerating expansion brought the concept back into the spotlight. What Einstein once considered unnecessary suddenly seemed incredibly relevant. Today, dark energy is often modeled as this energy embedded within space-time itself. Not a substance floating through space, but something woven into space's very structure. If that's true, the more the universe expands, the more space, and therefore dark energy, exists. Which raises an even deeper question about how the universe evolved long before our solar system ever formed. Long before the sun ignited and planets began forming, the universe was a very different place. It was hotter, denser, and filled with swirling clouds of gas and radiation. In those early epochs, gravity was the dominant sculptor of cosmic structure. Dark energy existed, but its influence was almost invisible. As the universe expanded and cooled, matter slowly began to gather. Tiny variations in density acted like seeds across space. Regions with slightly more matter pulled in surrounding gas through gravity. Over millions of years, these clumps grew into galaxies filled with stars. Inside those galaxies, vast clouds of gas and dust began collapsing further. Gravity compressed the material until the centers became hot enough for nuclear fusion. That's how the first stars ignited, lighting up the dark cosmic landscape. It was the same basic process that would eventually create our sun. Around young stars, spinning disks of leftover material formed. Dust grains collided, stuck together, and gradually grew larger. Like snowballs rolling downhill, these clumps accumulated more and more matter. Over time, they became planets, moons, asteroids, and comets. During all of this cosmic construction, dark energy remained in the background. Gravity was still the dominant force, shaping galaxies and star systems. But as the universe continued expanding for billions of years, something slowly changed. Eventually, dark energy would begin to dominate the large-scale evolution of the cosmos. Here on Earth, the influence of dark energy is completely invisible. The planet still spins through its familiar cycle of day and night. Seasons change as Earth tilts toward and away from the sun. Nothing in our daily experience hints that the universe itself is accelerating. That's because gravity dominates the structures close to us. The sun holds the planets in stable orbits, just as it has for billions of years. Earth's gravity keeps the moon circling overhead. These gravitational bonds are immensely stronger than the subtle push of dark energy. Imagine stretching a giant rubber sheet across a field. Now place heavy balls on top of it. Those balls create deep dents. Objects nearby roll toward those dents and stay trapped there. Dark energy is like a gentle stretching of the sheet itself, far too weak to pull objects out of those valleys. So our planet, our solar system, and even our entire galaxy remain safe from this cosmic stretching. Dark energy doesn't tear apart planets or pull apart stars. Instead, its effects only appear across the enormous voids separating galaxies. And when we zoom out to those vast scales, its influence becomes impossible to ignore. Over billions of years, galaxies that are not gravitationally connected slowly drift apart. It's like watching distant boats on a vast ocean move farther away as the water expands. The larger the distance between them, the stronger the effect becomes. Which means that to truly see dark energy at work, we have to expand our view to entire galaxies and clusters of galaxies. When astronomers zoom out beyond our galaxy, the universe begins to reveal its grand architecture. Galaxies rarely exist alone. They often gather in enormous groups called clusters. These clusters can contain hundreds or even thousands of galaxies bound together by gravity. Within these cosmic cities, gravity still reigns supreme. Inside a cluster, galaxies orbit the shared gravitational center much like planets orbit a star. Some drift slowly around the cluster, while others occasionally pass close to one another. It's a slow-motion cosmic dance unfolding over billions of years. Gravity keeps the entire system tightly bound together. But beyond the borders of these clusters, a different story unfolds. The vast spaces separating clusters are where cosmic expansion truly dominates. Across these immense distances, galaxies and clusters gradually move away from one another. Space itself stretches like a growing cosmic web. Imagine raisins inside a loaf of bread rising in the oven. As the dough expands, the raisins move farther apart. The raisins themselves don't grow, but the space between them does. The universe behaves in a very similar way as cosmic expansion continues. Over immense spans of time, this expansion reshapes the large-scale structure of the cosmos. Clusters remain bound internally, but the gaps between them slowly widen. Dark energy quietly drives this separation across the largest distances imaginable. And to understand where this mysterious influence began, scientists must look all the way back to the birth of the universe itself. To understand dark energy, scientists eventually arrive at the biggest question of all. Did this mysterious energy exist from the very beginning of the universe? Or did it emerge later as the cosmos evolved? The answer may be hidden deep in the earliest moments after the Big Bang. In those first fractions of a second, the universe expanded incredibly fast. Some theories suggest space-time itself carried certain built-in properties from birth. Just as water has natural behaviors like waves and currents, space-time may possess its own intrinsic energy. One possibility is that dark energy is simply a constant property of space. If so, it has existed quietly throughout cosmic history. For billions of years, its influence was small compared to gravity and matter. Only when the universe became large and diluted did it begin to dominate. Other scientists suspect something even stranger. Perhaps dark energy changes over time, like a slowly evolving cosmic field. Some theories describe an unknown form of energy filling the universe, sometimes called quintessence. If that idea is correct, the universe may still be revealing new physics, and so the mystery remains open. The cosmos may be governed by properties of space-time we barely understand. Dark energy could be a simple constant, or a doorway to entirely new laws of nature, which leaves one final question lingering as we step back and reflect on the meaning of it all. When people imagine the universe, they often picture brilliant stars and glowing galaxies. But most of the cosmos is not filled with objects at all. It is vast, silent space stretching across unimaginable distances, and within that emptiness, a mysterious energy quietly shapes the fate of everything. Dark energy reminds scientists that the universe still holds profound secrets. Something invisible fills space and slowly pushes galaxies apart. It doesn't shine, it doesn't form stars, and it doesn't interact with matter in familiar ways. Yet it dominates the large-scale behavior of the cosmos. Over billions and trillions of years, this cosmic expansion will continue. Galaxies beyond our local group will drift farther and farther away. The night sky of the distant future may grow darker as those galaxies slip beyond view. The universe could become a far lonelier place. And yet, here on a small planet orbiting an ordinary star, a curious species has begun to notice these enormous cosmic patterns. Humans have learned to read the faint signals carried by distant light. Through them, we glimpse the invisible forces shaping the universe. Dark energy is a reminder of how much remains unknown. Even the emptiness of space may contain hidden layers of reality. As the cosmos continues its silent expansion, humanity keeps searching, trying to understand the quiet energy guiding the destiny of the universe.